Okay, so do I need to increase or decrease the frequency in order to get a higher harmonic? The last question I put on there was, as I increase the harmonic, what happens to the wavelength?
It's shorter.
Okay, so as I go to the higher harmonic, I get a smaller wavelength, because first it was twice this, then it's equal to that, now it's 2/3 of that. I'm dealing with a relationship here of, this is where the wavelength shows up. So if this gets smaller, what does that tell us about the, because that's the speed of the wave based upon tension and the linear density. That doesn't change based upon the how fast it's vibrating up and down. It's based upon the tension and the linear density. Both of those haven't changed. So if that's the speed of the wave, if my wavelength gets smaller, what does that say about my frequency?
It gets larger.
It has to. If this gets smaller, that has to get bigger in order to get the same value. All right. Let's find out if that's true. All right. As a matter of fact, we have cut our wavelength in half. So what frequency would you expect to have on the monitor right here? Pardon?
120?
Yeah. So if this gets cut in half, this gets doubled, and it should be somewhere around 120. Oops, looks like I'm starting over there. So basically doing this until I'm sort of at a peak there. It looks like somewhere around there. And I have 121.3 hertz on this. What would happen if I dropped the mass? If I took off some mass? What would be affected?
Force of tension.
Okay, so this gets smaller, which means the speed is smaller. If you recall in the hallway, when I increased the tension, it went faster. So if I decrease the tension, it should get slower. So the first harmonic should appear, well, if that gets smaller, it would need to be at a lower frequency to get the first harmonic. Let's see if that happens. So I'm just going to take 220 grams off. And I want a first harmonic. Not quite there, because the node is at this point. I want the node over here. That's like a first harmonic somewhere around there. And I'm at 46.8 hertz. So reducing the frequency indeed gave us a first harmonic again when we had less tension. Questions? All right. Let's take a small little break here. I'm going to grab the sound tube, and we will commence with the one fixed, one free. All right, so We're dealing with one fixed, one free end. A fixed end is going to be a node, thus when I have two fixed ends, we have two nodes on each end. A free end will be an antinode. So the simplest, the first harmonic, would have a node at one end and a free end at the other. That is the simplest. So the big question is, how many waves is that? Is it half?
So,
And you said no?
it's a quarter, isn't it? Which gets to the apex of,
A full wave looks like this.
Oh, yeah,
it
that's
gets to the apex of the first half. So it's a
Yeah.
quarter.
If you're going from node to the first antinode, that's only a quarter of a wave. So the length is equal to a quarter of the wave, or the wavelength is 4 times whatever that length is. Now, I'm sure you can find some stuff that I posted where I contradict what I'm about to say. Hopefully the newer stuff should not. This next one is the third harmonic. I called this the second harmonic for a while. But the next one is called the third harmonic. So starting at a node, I want to end at an antinode. It's the next pattern that we can get, but it's still called the third harmonic. In essence, how many wavelengths is this?
0.75.
Yeah. It's 3/4 of the wavelength. The fact that I go from here to here by multiplying by 3. So that's why it's the third harmonic. So lambda is equal to 4/3 L. And we'll go ahead and do the fifth harmonic. And in your own mind, you should have an idea of what this is going to look like. And how many wavelengths is that?
1.25.
So the wavelength would be 4/5. Notice, just like with the last one, every time we went to the next viable harmonic, we added a half a wave. So I got a quarter here plus a half, quarter plus a half is 3/4, plus a half is 5/4, plus a half would be 7/4, and so on. Now this idea that we skip the second harmonic and the fourth harmonic, sometimes textbooks will deal with that by doing overtones. This is the first overtone. This is the second overtone. I tend not to use overtones, but that if you don't like skipping numbers, go for the overtones. So, given this, let's make our predictions. I know that the speed of a wave is frequency times wavelength. We're dealing with sound this time. What's the speed of sound?
3, 4, 3 meters per second.
34 what?
3?
Meters per second? It's somewhere around there. It does depend upon the temperature of the room. This is probably good enough for what we're doing. For every degree Celsius, it increases, the speed of sound increases by 0.6 meters per second. And room temperature is roughly somewhere around there. equal to, well, we need to figure out the frequency. This time we're gonna pick the frequency and then we will predict, we'll set the frequency and we'll predict the wavelength. All right, I'm gonna create the frequency using a LabQuest that actually seems to be holding charge. This is 1,000 hertz. Now, if it's too loud, we're not gonna hear the resonance. So I'm gonna drop. There we go. Drop it down to 50%. Let's see what, 4, 5. Wow. Oh. Let's see. Might have to drop it down more, but we'll go with that for now and see what happens. All right, so if I'm picking 1,000 hertz, what would the wavelength be? So using that equation, I get 343 meters per second is equal to 1,000 hertz times the wavelength. What would the wavelength be?
0.343.
Units?
Meters.
Yes. All right, so about 34 centimeters. I know for the first harmonic, the length should be 1/4 of that. So the length would be 1/4 of the wavelength, so for the first harmonic, so that's 1/4 times 0.343 meters, which is 0.08 575.
Yeah.
Okay. Now, what would we expect to hear? Well, what we would expect to hear is that if I have a harmonic, because the wave's going down, hitting the water surface right here, that becomes a node. That's the fixed end. The wave flips direct or inverts, comes back, interferes with itself. When I'm at a harmonic, I should have an antinode here at the top. What would an antinode sound like compared to not an antinode?
It would be quieter, uses a lower amplitude. Or,
That's a lower amplitude?
oh, I got node and antinode backwards. It would be. Wait, can you repeat the question? So the
What would an antinode sound like?
Would sound louder.
Yes.
The higher end.
So when we hit, so if we hit the frequency or hit the right length, it should be louder. Now, to adjust the height, we adjust the amount of water in that. The water level in the pipe here should be the same water level in the reservoir. So if I have enough water in here, I can adjust the height of the water level just by raising and lowering the cup. Simple enough. Here's the big downside, just to give you a heads up. This thing right here that the reservoir is sitting in is metal, and it's not blunted metal, so that when I move this up, there might be a loud screeching noise of metal on metal. So first let's get some more water in here. All All right, it's not raised going up very much because this is still down here, so here we go. I'll try to do this quietly. And so, and this is something from chapter 13 that we haven't done. But eventually the water will reach the same level because air pressure should be the same on both sides. Very slowly. Now, when you do an experiment like this, you need to make sure there's a trash can nearby. Now, I'm fine here. If we wanted to take it down there, we might have to quickly dump water out of the reservoir. And as usual, there's some sort of scum sitting on top. Now, another thing about these is that they have this measuring tape on the side here. So you could easily figure out what the measurement is. Unfortunately, or for some reason, 0 centimeters starts 2 centimeters below the top. And I haven't figured out, they were consistent, all of them did that. The older ones didn't, but these all do. And I'm not sure why. But whatever measurement we have on here, we need to add 2 centimeters. And I probably should have picked a lower frequency. But, whatever. All right. We delicately balance that there. That's 7 centimeters. We need 8, so 8.5. Let's see how close we get. Yeah, it's still too loud. And then we drop it down again. There's a stylus somewhere. Drop it to 20. Sounds just as loud. All right, 5%. There you go. And it looked like it did it when it, I assume you could hear it suddenly got very loud very quickly. All right, anyone not hear it? I'm getting blank looks. You did not hear it, okay. There's a small change there. That sounded far more distinct than last time. Alright, drop it. That small little bit right there was it. I still feel like this is too loud. So it looks like it's just shy of 6 centimeters on here, so add to 8 centimeters. Looking pretty close to what our prediction was. All right, I'm gonna choose a less annoying frequency. Let's go for 400 hertz. What will the wavelength be, and what will L be for the first harmonic? While you're calculating that, I will change this to 400. All right, anyone have values yet?
0.8575.
So length is what? Or wavelength?
0.8575 meters.
75 meters. And therefore the length,
0.21, 4375 meters.
40, 30, 75. I personally cannot see that level of precision. So somewhere around 21 and a half. Which is gonna be